My project was aimed at improving heuristics which are used to solve everyday problems, from packaging products efficiently to linear programming. An improvement in heuristic efficiency would result in less computing time and costs. While researching evolutionary algorithms, I came to the realization that evolution is inefficient in terms of problem solving. Imagine that an entity has both beneficial and damaging mutations, the later which nullifies the beneficial. Although the beneficial mutation was generated, it isn't recognized until later on. While this problem is most directly related to evolutionary algorithms, it has implications for other search methods. Could there be a way to fix this parameter conflict? My solution was to apply a heuristic to smaller groups of parameters or traits within a problem at a time, and then evaluate the score. This is unlike searching the problem as a whole, as it has the ability to recognize the best solutions for individual parameters. After studying the problem, I formulated a hypothesis. The efficiency can be increased with smaller group sizes only if the parameters being manipulated are unrelated. I later found out that my hypothesis touched upon the building block hypothesis, an explanation of genetic algorithms performance, which states that efficiency is increased by searching building blocks individually. I tested my hypothesis with one problem in which traits were dependent on each other and in another they were independent. For each problem, I tried two approaches, hill climbing and brute force searches. I ran each heuristic for different group sizes or number of parameters searched at a time. What I found reaffirmed my hypothesis. For the parameter independent problem, the smallest group size performed the best, resulting in a score 46 million times better than the large group size for the brute force heuristic, and 21 times better for the hill climbing heuristic. In the dependent scenario, the smallest group size performed 108 times worse than the largest group size for the hill climbing algorithm, and 12 times worse for the large group size for the brute force searches. What shocked me was that I had discovered that in the dependent scenario, the only two programs which found an exact solution were for the group size of 3. The data has shown that searching individual dependent parameters will result in decreased efficiency, therefore the building block hypothesis is flawed. But surprisingly, for some parameter dependent problem, the optimal group size is not the largest because the context of all parameters is unnecessary. I am wondering, what would the optimal group size for other dependent problems, such as the n-queens problem, be?